Okay, welcome everyone. How's it going? Hopefully the people online can hear. If not, send a message to the group me and we'll try to take care of that. Administratively, are there any questions? Okay, so there should be another in-class assignment that's due by midnight tonight. And then we also have another assignment that will be due before the next class, which will come on live later today. Okay. Any questions? I see the group me has been lighting up, which is good in some respects. Okay. Okay, all good with the video. Great. So, and they can, those that are not able to join us in person are able to hear what's going on. Yeah, but what are your thoughts? What are your thoughts at this point? Very quiet. It's okay.
Thoughts regarding what?
How we're doing in the class? Yes.
It's getting harder.
It's getting harder. That is true. That is very true. I agree. And we will be continuing to accumulate information that we continue to need to use on problems. At this point, we've really been focusing mostly on axial loading, and today we'll talk about normal loading. And that was kind of, remember in the first session we had, that was the bar, essentially, right? In a little bit, we're going to get to torsion. We're going to talk about shafts, and then we'll talk about beams. And it is, how do you say it? Getting things straight with the bar is kind of fundamental with these normal stresses, because once we start adding shear stresses, and then once we start combining them with each other, it gets even heavier, okay? It gets harder. It's okay. It's okay. Send me messages. I can't respond to all the group me's. Thank you for those who are looking out after each other. I appreciate that. And one thing to keep in mind is that there are also many example problems that you can look at. They're on Canvas. There are essentially homework assignments from the past 4 times I taught the course. So you're welcome to look at those, and then you have the previous exams on the website as well. So there's a lot of information. In fact, it may be a little bit overwhelming with all the information now. At least it would be for me, and sometimes it is for me, as you can see, negotiating, getting the lectures and getting the sessions up and running appropriately. So before our exam on the 24th, I would, though, suggest that at least you do, or at least you're very familiar with the problems on the previous exams. Okay? Now, I can, if you guys ask me and if I remember, I'll try to say, oh no, that's not fair game. We didn't cover that. But sometimes I think the question makes it obvious, like, obviously, you know, we haven't done torsion yet, and there are questions on torsion on those on exam 1, so that's not going to be, you know, you wouldn't be expected to do that right now. But by the 24th, yes, you should be, you know, we'll be up to at least that point. Whether or not we get to some of these transmission problems, which can be a little bit tricky, is debatable for this first exam. Okay. All right. And you know, most of the problems that we've been doing, the in-class assignments and also the assignments, have been very similar to the notes that we have here. Very similar. We're starting to get into a few that are not that similar, but guess what? Some of them are from the exams, so you have those resources as well. Great, thank you. Let's keep the dialogue going. So today we're going to have a brief recap from session 6. Which is what we covered last time, material properties. And then we'll go and look at volumetric strain and dilatation or dilation. We'll get to bulk modulus, which is related to volumetric strain. then have a little bit of a discussion on safety factors, get back to kind of the bar, some axial loading problems, and thermal strain and stress on a bar as well. Okay. So the last time we were together, we discussed some of the things on this slide. We discussed ductility, and we discussed how you could tell how ductile a material might be after a tensile test based on how much it elongated before it ultimately fractured, or how much the cross-sectional area changed where it broke. We also discussed how you can figure out toughness, which is kind of related to ductility. Although we also discussed how maybe you have a material that has quite a bit of toughness, but still suddenly breaks quickly. And some of the advanced glasses might fall in that category. We discussed two simplified material models, the linear elastic, perfectly plastic model, which had the horizontal plateau for yielding. And we also discussed the linear elastic, linearly plastic strain hardening model that had a slope, and that was something kind of like what we see here. Modulus of resilience is this area under the elastic region of the stress strain curve. And then modulus of toughness was, it's not shown here, but was, or it is shown here, there it is. Okay, it's everything under the stress strain curve until break. And we discussed Poisson's ratio, and then this general approach to solving problems in mechanics. And I'll attempt, when I can, remember to kind of lay things out in terms of equilibrium, geometry, and constitutive equations. Okay, so a couple of errata. So thank you all. I verified with my wife as well. I was wrong, okay? In the Princess Bride, yes, they use suction cups. It was something off the cuff that I was thinking, oh, you know, it's like when you elongate me, right? And I was like, you know, I was thinking torture and dark in a basement, and Princess Bride just suddenly came to mind. I hadn't anticipated talking about the Princess Bride when I came into the session last time. That's how some of this works. Some of this is a little off the cuff. But I'm sure you can think of other references, or other, you can conjure up in your mind other situations where you might have something that's stretching a material out. And thankfully, it was not that gruesome in The Princess Bride. It's a very age-appropriate, very friendly movie. And then over the weekend, I had, and actually on Saturday, there was an issue with my calculation for an area and a conversion, actually in the same denominator. I was surprised. So that was an example 6.5. That's been corrected also in Colab and in the notes. If you want to, I don't know. There's just, it's one little change because I didn't actually run through all the calculations in the PowerPoint, but I did report the resulting values, and they were off. And then there was an issue with section 6, Q6, but that was corrected last Saturday. So thank you for your feedback in the group meeting. So keep it coming. So let's talk a little bit about volumetric strain, or dilation and dilatation. And it's probably becoming a recurring theme, but what do? When we want to think of a material element, we draw a cube. Okay? We draw a box. And here is a box. This one is not even drawn by me. It's something that you can find on Wikipedia. And this box has a volume associated with it. When we put out the lengths of the sides. Now, something, just to keep in mind, this is following the right-hand rule. This is dx, right? So in reality, if you think about which axis is the x-axis, it's this one right here. And if you think about which axis is the y-axis, it's this one here. Okay, sometimes we get a little bit twisted, but those are the x and y axes. And then, this one's usually more straightforward. That's dz, so this is in the z direction. Okay. So we have our box, and then we apply normal stresses to this box. We'll call them sigma x, sigma y, sigma z. Okay. So I think this is going to be our last session for a little while where we talk about stresses without mentioning shear stresses. Okay, so these are sigma x, sigma y, sigma z. And we can apply them like you see here. Now, when we do that, what we're saying is the box can change its volume. So more or less, with these applied stresses, axial or normal stresses, that box that was originally kind of dashed inside has now become larger in volume. Now, what are the change in lengths of the sides of the box? So, without even using a constitutive relationship, just thinking back to the definition of what is normal strain, what is axial strain, we can realize that if we have the strain, right, which is usually a small fractional number, and we then add it to 1, right, that's like saying, hey, you got a 5% raise, and I want to figure out now what the new salary is. Okay? It would be 1 plus 0.05%, or 1 plus 0.05, right? It's 5% raise, times the original length. So that's what you're seeing here, okay, with these lengths. And the new volume, okay, can be written as V plus delta V. All right, so that's using kind of this idea here, or V naught plus delta V. And what we have here then is the product of all these sides, right? That's volume. And this is what it then can be rewritten as. If we want to focus on just the change in the volume, what we have here is this big thing, right? This V naught plus delta V, all right, minus the V naught. So V naught was the original volume, okay? And the original volume we wrote out up here, right? That's this dx, dy, dz. So we want to simplify this, and I'm not going to prove out every part of this, okay? But what you see, if you were to factor this thing out, what would you get? You would get a 1 and then a bunch of other terms, right? You apply FOIL, and then you distribute that resulting nastiness times the 1 plus the remaining epsilon, right? So you're going to get a 1, and then you're going to get some epsilon x term, some epsilon y term, some epsilon z term, okay? And you'd also get some like epsilon x, epsilon y, epsilon z. You get some cross terms as well. Well, a small thing times a small thing is a smaller thing, okay? So what we've done essentially is said, hey, we're going to ignore the cross terms because they're going to be smaller than these already small terms, and write out the volume like this. So this is an approximation. And it's a useful approximation. We'll use it a couple times, 2-3 times today. Now, dilatation is the change in volume over V naught. What does this kind of look like? It's like an E, but it's not epsilon, right? What does it kind of remind you of? Reminds you maybe of strain, right? A linear strain. Linear strain, like an epsilon, is a delta L over L, okay? And this is now a delta V over V, or delta V over V naught. And we have the delta V right here. Okay, this delta V is equal to, or about equal to, approximately equal to this term over here. But we're dividing by V naught, which is this over here. So now what do we get? We get epsilon x plus epsilon y plus epsilon z. That's interesting. Also, like linear strain, this unit, or the units of E, the dilatation, are unitless. Okay? There are no units here. Okay. Now, you remember this? This is our relationship that we got from looking at the effect of the Poisson's ratio on strain in multiple directions. Okay. And what we said is that, hey, if I pull in X, I shrink in Y and Z. If I pull in Y, I shrink in X and Z. Okay. If I pull in Z, I shrink in X and Y. Okay. So that's the Poisson ratio right there. And then this right here is Hooke's law. Okay, the epsilon x 1 over, or you have Hooke's law essentially being applied to this whole thing because, what we're going to get are stresses here. Okay. And we want to get back to strains. Right? Or, vice versa. So sigma is equal to E epsilon. So you get it, right? I got this dilatation quantity here, E, and I've got these constitutive relationships that I had before. We combine them all together, and we get this. All right? So, yes, this is epsilon x, right, plus epsilon y plus epsilon z, and we have these minus nu, okay, sigma y plus sigma z, but I'm going to have another sigma y from over here. I'm going to have another sigma z from over here, right? So I'm going to end up doing minus 2s of these guys, of those stresses, okay, across the board. And I still will have these terms, the sigma x, sigma y, sigma z times 1 over e, and that's what you're seeing with this, with both this and this. Okay? Any questions? Right now, just a lot of substitutions. So, why is this information, this is just copied from the previous page, why is this information useful? Maybe you argue it's not very useful. Well, what we're saying is we can calculate the change in volume now of a cube, right? If we know what the stresses that are acting on it might be. And so you get, sigma x, sigma y, sigma z, then we can calculate dilatation, right? And we can know what the change in the volume is. Now, what is hydrostatic loading? What do you guys remember from hydrostatic loading? Someone, I'm talking a lot. So what do you remember from hydrostatic loading? You can spit out equations or spit out concepts. I'll accept either. What is hydrostatic loading, really? Think back to maybe some physics problems. Yes?
Does it have to do with like Newton's third law? I'm not exactly sure.
Okay, so you could say, sure, for every action there's an equal and opposite reaction, okay, and there's some action-reaction pairs, and yes, Newton's third law is going to apply. True, yes. Yes, so that's something you remember, right? Pressure varies with depth. As you go deeper underwater, and then we're saying we're going underwater, right? And as we get farther from the surface, the pressure increases. Anyone remember what that funky equation was? Yeah, rho GH, right? Okay. Now, how would hydrostatic loading Okay, so we have this pressure idea. How would pressure relate to stresses? Yes. Yes, right. So I didn't quite catch the first part of that, but yes, the object is going to feel the pressure on all sides, like you said, and you get the idea, right? Pressure has units of pascals. Stress has units of pascals. Well, what do you know? I can just substitute in all of those P's, all right, into the sigma x, sigma y, and sigma z. Okay? And by our convention, those are going to be acting inward, and so pressure is going to be what we equate to negative stresses, or negative pressure is equal to positive stresses. Good. So all these stresses can be set, or the inverse of these stresses can all be set to P. Yes? Well, that's an interesting question. If I had sigma x's and sigma y's and sigma z's that were not the same, okay, you could imagine, for example, squishing in the x direction, right, and then getting actual expansion in the y and the z, right? But like you're suggesting, if I apply, right, pressure from all sides at the same time, and it's the same, yeah, I'm going to be causing there to be contraction, right? And that's what you see with the math too. Okay? If I make all these quantities the same and I make them all negative, this is a positive quantity, this is a positive quantity, right? Because nu can only go to max 0.5, right? We'll talk a little bit about that. So the dilatation, okay, this change in volume divided by the initial volume is going to be negative. Okay? So yeah, you're going to contract. So dilatation in terms of pressure can be written like so. And the bulk modulus is the term that people use to report these relationships, okay, between dilatation and pressure. Okay, so here's a K, all right, and here's the pressure, and here's the inverse of the dilatation. Okay, and so we can think of this bulk modulus as essentially being 1 over the coefficient, right? That so this, remember, there are 3 of these guys, so that they have a 3 over E, 1 minus 2 nu, right? Right there, that ends up being the bulk modulus. Okay? So this is kind of like a volumetric springiness, essentially. Okay, right? We have spring rates, we have spring constants, but it's not really a spring rate or spring constant. It's actually more like an elastic modulus. Okay, because what, we think of it as a spring rate maybe, for right now, but look at the units again. We deal with a lot of pressure in this class, right? This is dimensionless in the denominator, and once again, the elastic modulus is in units of pressure. So this is something, probably worth writing down. And the next, but it's almost useless without this one. Okay? So P is equal to minus KE, right? So this is almost like sigma is equal to E epsilon, right, for the Hooke's law. But now we're talking about pressure and volumetric strain. Any questions on this? No? Okay. So yes, it has units well, this is dimensionless. This has units of pascals. This has units of pascals. And similar to what we see with many of the elastic moduli, it also is typically on the order of 10 to the 9 pascals. Now, we did talk about the Poisson ratio and its values, and if you look at the video from Efficient Engineering, it also discusses what happens when you have negative Poisson ratios. But for the materials, the solid materials we'll be dealing in this class, they're typically going to be positive and they will be less than 0.5. We begin to see if it were to be 0.5, what would happen? This K would essentially explode. And if it explodes, and so this is infinite, that means that you would have to put an infinite amount of pressure into the system to get it to contract. And that is also not very realistic. Okay, so here are some bulk moduli. If you like, you can run the code, which is available on the website. And aluminum, right? These are aluminum, steel, right? These are now elastic moduli that we're almost committing to memory. I do not remember bulk moduli, by the way. That's not something I would be like, hey, that one's like 70, 10 to the minus 6, or something like. No, I don't. Actually, that's actually not even this. I was talking about thermal. I was thinking thermal coefficient of expansion, which I also don't really remember. But so like the aluminum, its volumetric coefficient of expansion, which we'll talk about in a little bit, is like around 70 times 10 to the minus 6 per Kelvin. Okay. Here, okay, we see that. I mean, I guess it's not that hard to remember. If you think, all right, I'm going to do 1 minus nu, okay, and it's around 0.33, so that gives me something like 1 minus 0.66. That's not far off from, it's not close to, well, it's kind of like a third. It's close-ish, right? And these are the Cal values that have been calculated here. Okay. In fact, what did I do? Yep, I did. That's why I was like, that doesn't make sense. I wrote quickly, and I wrote incorrectly. Okay. Yeah, it's like, how in the world does the, did anyone else see that? How in the world does the elastic modulus and the bulk modulus come out so close if it's 2 in the denominator instead of 3? Okay. So the bulk modulus is a quantity that allows us to relate volumetric strain and, yes? Sure. Yes, that's right too. Thank you. Thank you very much. Okay. So let's do an example. If we drop a block made of aluminum with each side having a length of 1 meter in water that we pressurize up to 100 atmospheres, what is the change in the volume of the cube, and what is the change in length of one side of the cube? Finally, what would be the equivalent depth underwater to get to 100 atmospheres of pressure? So let's draw out our cube, and we say, okay, each length is L. We have pressure, we have questions about change in volume, about change in length, about how deep we have to go, and we have all this pressure acting on the system. if we take our general approach, okay, we might write out 3 columns. And sometimes these columns are a little bit sparse. Okay? There's not much to write there. But we can write for equilibrium that we have pressure acting on surfaces and we have balanced forces on these surfaces. So yes, if you want to be really, you know, how do you say it? You want to say, oh, you know, I have a change in depth from the top of the object to the bottom of the object. Okay, so I have a little bit more pressure acting on the bottom versus the top, okay, but it's pretty minuscule. Okay, it's pretty minuscule, and it's likely not going to. If this were a piece of aluminum, right, which has density, specific density of like 2.7, 2,700 kilograms per meter cubed. That's going to be sinking. Okay, so don't worry that, you know, there's maybe a little bit more pressure on the bottom. Okay, but it's still sinking, still going to be on the bottom, and we're going to ignore that change, that difference. We can think of geometry. Okay, and if we want, we can say, okay, it's going to contract on every side. We can write out the constitutive equations now. So what do we have understanding that the dilatation is equal to delta V over V naught. We have the pressure is equal to minus KE. Those are kind of our 2 go-tos here. We also have some information about the relationship between dilatation and these lateral strains, okay? Because they asked, or I asked, or we're asking, what is the change in the length? Okay? So we don't just want the change in the volume, but we also want the change in length of these sides. So we can write out that it's going to be 3 times, let's say, epsilon x, or 3 times epsilon y, or 3 times epsilon z, because it's the same in all 3 directions. Now, maybe some of you are like, hey, you know, I really want to change, I really want to go back and calculate the change in volume, okay, and then figure out what that would correspond to in terms of lengths. Okay? You're welcome to do that. Okay? This, remember, is an approximation that we have introduced because of the epsilon x, the products of epsilons being very small. Okay, so now we can say that epsilon x is equal to E over 3. All right, that's from here. We can say that the change in length is equal to L naught epsilon x. We can say that's L naught E over 3. And we can also say that the pressure underwater is rho g h. Okay, which one of you mentioned previously. So those are the equations. We have now change of volume up here, we have the change in length here, and we have a calculation for well, actually, I need to do one more thing. We need to do solve for delta H. Yeah, so delta H is equal to that. So those are the 3 quantities. So using a calculator or using Colab, right, IPython, we can write out the values that we have here and then put them in this form, being very careful with the units. Okay. So the 68.6 gigapascals, right, that's a K. So the way, you know, and there we have a little video on how to treat these things carefully. And am I perfect? No, I'm not. Mistakes. Usually, though, with some very careful analysis, line by line, unit by unit, I'm able to track my issues. Okay, and then the conversion between 1 atmosphere and kilopascals is 101. So 1 atmosphere is 101.3 kilopascals. Okay, so that's what you see here. And then we can solve for delta V, all right? And delta V, okay, is the dilatation times V naught. Okay, now, maybe another slightly, look, I mean, I don't want to spend too much time on this, right? But, you know, when you're doing volume, so we have 100 centimeters in a meter. So we cube that, that's going to be 1 million. All right, so multiply by 1 e to the 6, right? Here, what are the, you know, the units for delta V here are going to be in units of meters cubed, but that's a really small thing to write out. You know, that's a lot of 0.00. So we convert to centimeters cubed, and you know, 1 centimeter cubed is a milliliter as well. Okay, and then same thing with the epsilon x. We want to maybe convert to something that we can see a little more easily, so we can write it out as microns. So we're going to multiply by 1e6. And down here, when we do our calculation for the delta H, okay, we also can plug in appropriate units and conversions. Okay. Any questions on this? Yes. So, you know, you just pointed out that I wrote the the equation for the bulk modulus incorrectly, but if we were to give you the elastic modulus and the Poisson ratio, right, then you can calculate out the bulk modulus. Yes. Okay, so let's go ahead and now hopefully I won't forget the bulk modulus in the future, but it's it's this guy. It's E over 3 times 1 minus 2 nu. Oh, I don't know where it is. Oh, there it is. Yeah. E over 3 times 1 minus 2 nu. Okay. So, let's talk a little bit about distributed axial loading. Oh, no. First, oh, I skipped. First, we're going to talk about safety factors. I'm off here. Okay. So, what are safety factors that you might have encountered before? Or better question, or hopefully better question. Where do you think you've been in situations or you've seen machines that have some calculated safety factors? They may not spit them out to you, but where would you see machines that have, you know, some safety factor embedded in their design? Yeah, in the elevator, right? So you get in, you know, and you know, with your 5 friends, and you look at the little specification for how much weight it can handle, and you know, maybe you get nervous, maybe you don't, right? Depends on the size of the capacity of the elevator. And then has anyone, I don't know how well, and you know, that's gonna, what is that accounting for? That's probably accounting for a whole bunch of different scenarios, right? I don't know, maybe someone can Google. I don't actually know what typical safety factors are for elevators. I'm guessing at least 2, but I could be wrong. And you know, what could it be accounting for? Well, it could be accounting for some wear in the cable over time. Hopefully not. Yeah, I mean, the emergency brakes, right? Hopefully they will work, but it could also account for some issue with the emergency brakes when they do need to engage. You know, not necessarily being as new as they were when they were first installed, and so not handling as much weight. Maybe that accounts for people jumping in the elevator. Okay, anyone do that? That's fun. Okay, so you know, before yeah, so this was before 9/11. It was for sure. I remember being able to go into the Prudential building in Boston, and jump in that elevator. You know, you could just walk on, and that's like a, you know, it's a pretty tall building, and boy, you could get up pretty high or feel like your knees just got slammed pretty hard into the ground, okay, when that thing accelerated or decelerated. Okay, so we have this idea that you design for safety, okay? And it can be a little bit confusing when it comes down to a mathematical definition in terms of what are we dividing by what. So one way to think about a factor of safety, or a safety factor, is in terms of the load at failure divided by the allowable load in terms of forces. Okay, we can call stresses moments, torques, we can call them loads. You can put thermal strain on something, that would be a load as well, or a strain, apply a prescribed strain, that would be a load as well. But one definition is to say, okay, I calculate out when my structure will fail. Like maybe I've done experimental testing and I know, or maybe I've done a deep amount of analysis and I know it's going to break with this load. So that's kind of the physical limit. And then I tell people, this is what you're allowed to put on the system. So my elevator, it can really handle 3,000 pounds. I don't know. You know, I've been in the lab, I've run some simulations, I've done a lot of calculations, I've looked at the diameter of the cable and the strength of the steel in that cable, and I have an idea of, okay, this is how much it's really gonna be able to take before it breaks. But then based on the unknowns, right? So if I don't know how it's going to be loaded exactly, I'm going to lower that allowable force even lower, right? And you think in the aerospace industry, typically these safety margins or these factors of safety are lower, but it's supposed to be in a more controlled environment and also done with quite a bit of analysis, right? But like the example I think in one of the videos that's on the website, automobiles are going to have higher safety factors because we have us driving them. Okay? We have our New Jersey potholes. Okay? You have all kinds of slightly larger than desirable loads that are being put into the system. And you want to not have a catastrophic failure. Okay, another definition is to say, what is the stress at failure? Okay? And what is the allowable stress? And it can be in terms of a normal stress or a shear stress. Oh, I lied. Okay, we did have a shear stress here today. All right, there it is. So again, this is a stress associated with physical failure, and typically for uniaxial loading, which is what we've been focusing on doing, it's the yield strength of the material. And then you prescribe an anticipated or a specified stress for the operation of what you're trying to do. I think this can be confusing. There are just two ways to adjust your factor of safety. Okay, one is to increase the physical load that you're able to handle, okay, or endurance, and the other is to reduce the allowable load. Okay, so we'll see problems where maybe there's a little bit more focus on design, and if they say this bar is designed with a safety factor of 2, and the yield strength of the material in that bar is 100 megapascals. What is now the maximum allowable? If there's a safety factor of 2, the yield strength is 100 megapascals, the maximum allowable is Yeah, 50 megapascals, right? Or, right, let's say that I need to select a material, okay? And I calculate that the stress is going to be 100 megapascals. And I kind of want to make sure, and in order for the application to work, it's not just I'm calculating the stress, but during operation, this part is going to experience 100 megapascals. If I want a safety factor of 2, I got to find a material that has a yield strength of 200 megapascals. Okay? So there can sometimes the wording on these can be a little bit tricky sometimes. Okay? And designers, like we said, are going to specify safety factor greater than 1. Okay? Now, if anyone watches Veritasium, I think I'm allowed to admit that I like Veritasium. Okay. There's a good episode that describes what's called planned obsolescence or dynamic obsolescence. Right? And you're probably familiar with this. We're all familiar with this in today's world because we all have things that we would like to last longer, but they don't. And there's not necessarily a physical reason for them to stop working, but things happen, or bugs somehow get in, all right, in some types of applications, right? But I loved my Samsung, if you're listening, I love my Galaxy Note 4, all right, that I got like in 2014, and it was like just last year. Was it last year? Maybe it's been a little longer. Maybe it's been a year and a half now. I bought another used, which I got off Craigslist, right? But this now at least, you know, in the span of like 6 years, I guess I went from Craigslist to Marketplace. I don't know if that makes a difference, but yeah, I bought another used phone, right? That was like a year old, and but the Note 4 was a great phone, but over time and stuff, it just got really, really slow, unfortunately. Okay. Actually, I don't know what happened. Now it's completely dead. I was trying to use it like as a separate thing, and now it's completely dead. Anyway. Okay, so let's move to the topic that I thought I had inserted, but axial deformation in a bar. Okay, so let's remember Hooke's law, and then if you want to see the derivation, there's a YouTube video or Hibbeler's book that you can look at, but I'm just going to give you the result. So what is this saying? There are a few terms here. If you have an axially loaded bar, okay, and let's say you're going from 0 to L, so you're going along some length, and there's an internal force P and a cross-sectional area A, and the material has elastic modulus E, we can integrate this expression to get the displacement. So here's kind of the base example that you're already familiar with. A bar being pulled apart with some force P, and you're already like, I know the answer, right? Because we talked about pli, right? It's going to be PL over EA. But this equation can come to the same conclusion. Okay? So we go a little bit more slowly than just saying the answer is pli, all right? We say, all right, I'm interested in, let's say, B relative to A, that displacement, or I can think of it as the extension, okay, of AB, this member AB, and then I put in my constitutive equation here that relates force and deformation. And when we integrate this out, well, first, I guess before we integrate it out, sorry, we remember that the internal force is the same throughout the entire member. And then when we integrate it out, what do we get? We get that this is going to be px, all right? So just maybe we should say this. This is not times x. This is maybe a little bit confusing notation, but this is the notation Hibbler uses typically. Okay, I think it's a fine notation. No knock on the book. But this is a function of p is a function of x. A can also be a function of x. All right. So I plug these things in, and I get pli. All right. Pretty straightforward. What about a slightly more complicated problem? So let's talk about a distributed axial load on an axial member. So here is another bar, remarkably similarly shaped. And we go from A to B. And instead of having a kind of uniform force throughout the bar, okay, what we have instead is a P that grows. Okay. So like it's continuously growing, like you see here. Where you might see something like this in a system that's centrifugally loaded, right? Which I wanted to do the example in class today, but I think it will show up on the assignment. And this is from exam 2015, exam 1 from 2015. But when we look at this system, we need to take some cuts, and we also need to have something that describes this force. Okay, so this gradient, or this force that has a gradient in it, right, as we go from left to right, okay, is on the left side, it's all being counteracted by some combined force. Okay? And we can describe this force in terms of a linear increase. So like, just say P is equal to mx. And when we take a cut, okay, hold on. All right, so I didn't do that. I wish I had. Let me do it right now. When we take a cut, okay, we still have this R like so over here, okay? But we're going to have some internal P. This is the P, right? This is the same P that you have here. And this is varying as a function of x, okay? So if, I'm close, right? If my cut were like this, where I'm right here, right? I would draw a small p, okay? And if I'm farther along, going to the right, I have a bigger p, okay? The element still has to be in equilibrium, though. So I can have kind of this p of x function, all right? This is the external load, but I also have essentially an internal force, okay? That's being applied to keep things from accelerating left and right. Okay, so it's a little bit counterintuitive. So, when you do the integral out, what you get is that this expression is going to be ml squared over 2ae. Okay, just like this. Okay, let's do another example. We have a bar of length L with cross-sectional area A. It has density rho and elastic modulus E, and it's hanging from a ceiling. And we have gravity that's acting downward. And we're interested in the change in length of the bar. So, what might we do? Well, maybe we can write out our 3 columns, our equilibrium, our geometry, and our constitutive equations. When we look at equilibrium, what do we have? At a given location, okay, we're going to have this rho g a acting down, and we have the p. Now this is kind of a complicated expression to have. All right. We have, again, if you're just a little bit down from the ceiling, you might have actually quite a bit, okay, of force because you're very close to the R, right? And because you have the mass essentially of the entire rest of the object, okay, that's acting down, right? If I just took this object, right, rho GL, we're going to have rho GLA, right? That's rho G times the volume. That's the entire reaction force that we have here. So a safer way to do these problems, which is what I should have done, is sometimes to think in terms of going and exposing up. So here at this end, right, there's 0. This is just zero force acting on the end, right? And as we build up, okay, as we move up in the x, okay, we're accumulating more and more of this force. When we integrate this term, okay, well, we had to get to the constitutive equation, okay? When we integrate this term, right, we'll be able to figure out the total displacement of the bar. And these are supposed to equal out with each other, okay? And if we look at the units just quickly for this internal P, all right, what we see is that they do in fact come out to be newtons, all right? But we need rho times G times area times length, okay, times X right there is going to be the newtons. All right, so geometry, not much to write here. We're interested in the delta at the end. Constitutive equations, okay, this is our big one. And when we do the integration out, we get the following term. So if you plug in some numbers, okay, you'll see, well, even without plugging in numbers, you see that these A's cancel out. So there's not a dependence on cross-sectional area. And so you can make, if you're looking at the extension of an object, it doesn't matter if it's, you know, a very narrow cable or it's a large cylinder with a large cross-sectional area. The amount of extension that you get at the end is going to be the same. Okay. Let's go back and look at axial deformation in an indeterminate system. So this is one that we did previously, where we said in session 3 that if I have a force here and I know the stiffnesses of these members, we're able to figure out what the relative forces, what the regular relative internal forces are going to be in comparison to F, right? And we said if it's stiff on this side, K1 side, on the 1, section 1, right, it's going to have a lot of internal force. And if it's stiffer on this side, it's going to have more internal force, right? We also said we knew that the sum of the displacements has to be equal to 0. So if we go back and we kind of apply our 3 columns for equilibrium, geometry, and constitutive equations, we can attack this problem. Okay, but these are results that we got previously. Now, whether or not it was really necessary to put these 3 columns all together to do this, I think is debatable, as we'll see in a second. Okay. But here we have equilibrium that we're attempting to satisfy in this member. We have equilibrium that we're attempting to satisfy in this member here. And if we look at equilibrium on the first member, we just say, okay, the internal force F1 is equal to R1. If we look at the internal force in section 2, we'll say that F2 is equal to minus R2. And we can also look at the geometry, which we're not going to use too much here, okay? But we know that the change in displacement here plus the change in displacement there is going to be equal to the change in displacement from there to there, which is equal to 0. Okay. Let's write out some constitutive equations. And back even when we were doing this problem in session 3, we said that F is equal to K delta. Now, and after, let's see, in session 5, I think, we described delta is equal to FL over EA. Or maybe it was session 4. So what we're really going to do is reside right here. We're going to say, okay, delta is equal to F over K. So delta 1 is equal to F1 over K1. Delta 2 is equal to F2 over K2. And we want to know the ratios between the lengths. And you could have maybe remembered that at some point we said that K is just equal to EA over L, and I could have done it that way, and that would have been fine. But here we're going through and saying, all right, I have this constitutive relationship, I have this constitutive relationship, I have this equilibrium occurring, and that I know what the internal forces are, and what they are related to R2, but I'm not actually even using R2, so even this is maybe not necessary. And then we can say, okay, K is equal to EA over L1, K2 is equal to EA over L2, and what I asked here is what is the ratio between the lengths? So we have L1 over L2 is equal to K2 over K1. So could you have done this without even looking at this problem? Yeah, maybe, right? Because essentially it said, hey, look, these are the spring constants, if these are the spring constants, and I can tell you immediately what EA over L1 is. But the point here is that you can, or I can, we can begin to solve problems with axial deformation using our additional knowledge that we have in terms of delta being equal to the integral of PL over EA. Okay, final topic. So let's say we have a bar, right? Another bar. And it's at a given temperature. And has a given length, has a given cross-sectional area, and it has some material properties, like a coefficient of linear thermal expansion. What's going to happen if that coefficient of thermal expansion is positive? Well, as I heat up the bar, right, it's going to extend its length. So some terms that we might use to describe this bar, all right, are the initial length, the change in length of the axial member, the linear coefficient of expansion, okay, may be given by alpha or alpha L, and then a change in temperature. So, you've probably seen this from some of your other classes, but we say that the change in length is equal to some alpha, okay, times the change in temperature times the length. Now, look at this. This is kind of fun. If I divide by L on both sides, I get delta L over L. What is delta L over L? That's the strain. Right? So now I have an expression for the thermal strain that a bar can experience. This is with no reaction force or no constraint on one side, right? This can just expand. So, is it possible to have a system where you have strain but no internal stress? Absolutely. This is one of those, if it's a free-ended bar, that's the case. So there's no internal stress, but it still gets longer, just with thermal expansion. So if we look at our system and we have a free end, we would just say, hey, the internal stress is 0. But the strain that we're experiencing can be given by alpha L delta T. And the strain is, again, a unitless quantity, and it can be acting at any location along here. It's going to be a constant value along the length of the bar. Now, here are some linear and volumetric coefficients of thermal expansion. Do you remember, if you look down here, okay, you remember we had this definition at the beginning of today where we said dilatation is equal to delta V over V naught, and we said it's equal to these 3 strains, linear strains added to each other, or about equal to it. That means that dilatation is equal to 3 times the thermal strain in one direction. But it's all, if it's a cube, it's all going to be the same. So, if someone hands you a volumetric, okay, and so that it's equal to 3 alpha L delta T, and what do we see? We see that if you have instead a situation, okay, where you want to describe the volumetric change, right? So I plug in alpha V here, right? Okay, or I plug in alpha L here, right? And I get 3 times 1/3, right? I can think of a volumetric strain coefficient as just being 3 times the linear strain coefficient. And so this table does a pretty good job of showing that, okay? Kapton has a linear coefficient of thermal expansion of 20 times 10 to the minus 6 per Kelvin, right? And then the volumetric one is 3 times that. Any questions on this? Good. So now, let's look at the linear expansion of a heated bar. Here, we have bar. It's going to have 0 stress in it, and we can apply a temperature. We're going to say we're going to go up to 212 degrees Celsius. So 212 degrees Celsius from 20 degrees. So there's a change of 192 degrees Celsius or a change of 192 K. Either way. Don't worry about like that 270 whatever conversion between Celsius and Kelvin. Okay, so now we know the elastic modulus, but Do we need the elastic modulus? Not really. We have a volumetric coefficient of expansion of 69 times 10 to the minus 6. That's great. Okay. What is the change in length of the bar? Well, we can divide either way, right? We can divide that by 3 if we want. So here, delta is equal to, this is a linear delta. It's just the volumetric delta divided by 3. Okay. And it's got these units of 10 to the minus 6, so times 1 e to the 10 to the minus 6, times the change in temperature, times the length. All right, so we can say that the length, it changes not by, this is only 1 meter, and it actually changed by about 4 millimeters. Okay, so that's something that you might actually be able to measure and see. That's like almost half a centimeter. Okay, now, there's one thing I did not get to, and I would like to discuss what happens when we have a constrained bar. Okay, so let's say that we have a bar. I'm gonna actually, let's do it this way. So we have a bar. Okay, that's constrained. It has some length L. Okay, and we're going to say there's some delta T here. Say it has some elastic modulus. Okay. It has some alpha L. Okay, some linear coefficient of thermal expansion. So we can kind of use our force method here of superposition. In other words, the bar will go past if left unconstrained. All right, so this is the unconstrained case. Okay, and we know what that is. We know that extension, that delta, is just going to be the alpha L delta T times the initial length. But since it's constrained, it can't really do that. It can't just extend. Okay, so what am I going to do? What are we going to do? We're going to apply a load from the wall, okay, to get it to go back. So we're going to say, no, I don't really want you to do that. I'm going to say that you're able to go, but not really, because I'm going to apply a wall force to the end. We'll call this delta T, or delta T. And we'll call this one, and if I draw it this way, okay, delta W, all right, it's in the opposite direction. So what am I going to get? I'm going to get, if I look at geometry now, so geometry, I have that delta T minus delta W has to be equal to 0. Okay? Because those walls really aren't allowing there to be any change in length. So I need to think about how much force I have to apply to counteract what's happening with the thermal expansion. Well, what's the relationship between delta W and force? Well, delta W, right, is going to be FWL over EA. That's the Flee equation. So now, what we can do to figure out FW, okay, is put these things together. So I have alpha T alpha L delta T L, okay, minus, that's equal to 0. And so to solve for FW, what do we have? We have alpha L delta T L times EA, but also divided by L. So this is a case where thermal strain can lead to a reaction force, which also, did I make a mistake in my math?
Yeah, doesn't the L in the denominator cancel out?
Oh yeah, that's right. Thanks. So the force, right, can counteract this thermal strain and can be considered a stress, right? So we talked about thermal strain. Now, what's the strain in this system? If it's constrained, huh? Right, so what is the strain? The resulting strain is 0, right? So now we have a situation where the thermal strain is equal to 0. What about the stress? What's the value for the stress? Well, we calculated it out almost, right? The thermal stress is going to be, in this case, if we use our convention, right, that's a minus, so minus FW over cross-sectional area. So that is going to be equal to minus alpha L delta T times E. You can begin to think of other more complicated problems, which you can see on an exam, for example. If you have materials with different properties that are right next to each other and are placed in between walls. Or you can think about situations where there's initially a gap between the bar and the wall, but then it expands and then it hits the wall. Okay? So those are some of the examples that are available. Thank you guys for your time, and I will see you all in a little bit. Have a good one.